So in the previous video, we talked about how we can construct a lattice structure from the function field. So that means in the beginning, we fixed our function field with genus G, and we fixed finitely many places. In general, it's going to be the rational places, but we denote it as a tuple by putting an order on it. And here we denote a place inside of this curly P by Pi. By use of notation, we will denote it sometimes as a set or subset of the set of places, but in general, we need to consider as an n-tuple. And we consider a set OP star, which contains the functions whose poles and zeros are exactly a subset of curly P. And we consider a group homomorphism which maps to Z2 their valuations times the degree of places. For the ith coordinate, we consider the place Pi. And indeed, by using this notation, let me fix let's say some notations. By using this construction, let me fix some notations. Sometimes we identify the principal divisor of the functions inside of OP star by its image. And to simplify the notation, we didn't denote the length of its image simply by length of Z. Actual length of Z doesn't make sense, but I mean, in general, for the length of Z, we consider its image. And for the lattice theory, we have the notion of what is called the even lattice or the even vector. Let me say that a lattice L is called even if every vector has even length. It's an even integer for any vector V in L. So the first observation we will make is that the function field lattices are even lattices. So that means we will first investigate the length of the vectors and consequently its minimum distance. So the first proposition will tell us for all functions in OP star, their length is even. So consequently, function field lattice delta P is an even lattice. And the second property will be if we have a function in OP star but which is not a constant, then because if it is a constant, its minimum distance, like its image is going to be a zero function, right? Because I mean, if Z in FP star, we know that VPI of Z is going to be zero because it has no zero and no pole. So the image will be the zero vector. So this is why we consider a non-zero constant. Then its minimum distance is bounded below the square root of 2 times degree Z. Here recall that degree Z denotes the degree of the zero divisor or the pole divisor. And the equality holds if and only if the zero and the pole, of Z in the rational function field fq of Z splits completely in the extension F over FQ of Z, but it splits completely. What we want to say is that if we are given place P in the rational function field, and when we look at its extension places, we have exactly n many extension places where n is equal to this extension degree. So by the fundamental equality, what we can say that its ramification indexes, like for the extension places, its ramification index and the relative degree should be 1. So that means we have n many extension places. And the minimum distance of our function field lattice is bounded below square root of 2 times the gonality of our function field. Recall that the gonality was the smallest extension degree of F over a rational subfield. So, okay, let's try to see if we can prove these properties. And for the first property, I'd like to see that our function field lattice is an even lattice. Let me take a function in the OP star, and let me denote its principal divisor is a combination of AIs and the PIs. And suppose that we have n many, like these are the all poles and zeros, so the AIs can be positive or the negative. So in this case, if we look at its image, it's recalled that its image is defined as like, for the ith coordinate, we have the PIs at like the valuation at with respect to discrete valuation map be PI degree PI. So the length of its image, for the simplicity, we denote by length of Z. Indeed, its square can be written as A1 square degree P1 square an square times square of degree Pn. So here, actually, we use some fact from like basic arithmetic. Indeed, for any integer Z, observe that c square minus c, c square is exactly equal to c in modulo 2, because c square minus c is c times c minus 1. And like 1 should be like the odd or the even, so this is always equal to 0 in modulo 2. So this is why we can write any integer, we can write the square of any integer as itself in modulo 2. And here we use this property. So that means we can write this equality equivalently A1 times degree P1 an degree Pn in modulo 2. So if it is the case, and if we know that the degree of Z, so indeed, like this is this sum denotes the degree of our principal divisor, right? And the degree of the principal divisor is always 0. So that means we get the equality. So this is why the length of every non-zero vector is even. So this is why our function field lattice is an even lattice. And to see the second property, so which tells us this minimum distance is bounded below the square root of degree Z. In this case, let me separate, let me denote the 0 and the pole divisor of Z for any transcendental separately. So again, let me consider a function in OP star, which is not a constant. So if it is not a constant, this should be transcendental, right? So if it is transcendental, we know that the extension degree f over the rational function field generated by fq and z should be finite, and this is exactly equal to the degree of z. And by the degree of z, what we mean is the degree of the zero divisor or the pole divisor. And let me denote this zero divisor by the zeros Qi's, and let me denote the pole divisor by the poles Rj's. So here Qi and Rj are distinct places. In P, it should be in the curly P because thanks to this choice. And here we know that the zero divisor and the pole divisor are the positive divisors. This should be positive integers. Again, let me compute the square of the length of Z in terms of this Bi's, Cj's, and Qi's and Rj's. And by the definition of the length, we can represent it as the sum of Bi square times square of the degree of its zeros plus square of Cj's times the squares of degree of its poles. So like always, we know that this is a positive quantity and this is always bigger than or equal to the sum of Bi degree Qi plus sum of Cj times degree Rj. And indeed, like if you recall the definition of the degree of the zero divisor or the pole divisor, so this is the degree of the zero divisor, this is the degree of the pole divisor. So it is indeed 2 times, and they are equal to each other. So this is why this is equal to 2 times degree of Z. And here the tricky part is that the equality holds, like if we have, like let's say the equality here, and since these are always like the positive quantities, this happens if and only if the coefficients of the multiplicities of poles and zeros, which are denoted by Bi's and Cj's, should be 1, and they should have the same degree, like the poles and the zeros should have the same degree for all Ij's. And then like, because otherwise we lose the equality in this expression, we get this strict inequality. But this is not the case we want to consider. And this can happen if, like, that means if you consider, like, this is the tricky part. In FQFZ, we know that Z has a zero as like PZ, and Z has a pole as P infinity. And in F, we denote the poles of Z. By the way, this is like the zeros of Z in F in terms of Qi's. So that means PZ, like the zero of Z in the rational function field, has extensions Q1 up to Qs. And similarly, the pole of Z in the rational function field has extensions Ri's, Rj's. And having these coefficients as one means that, is that because we in the last lecture recall that the zero divisor of F in the base field can be determined completely in terms of the conorm. And conorm was defined in terms of the ramification index, right? The conorm of the zero divisor in the rational function field gives us the all zeros of Z in F, and that was determined by the ramification index. So that means having this BI means that like we have the ramification indexes as 1. And having the degree 1, so this is also another tricky part. If you have a place, like in the extension field, F prime, let's say Q prime, we know that there exists a unit place, but if this is rational, this place should be also rational. So like in this setting, you should be careful about it. So that means we also have the ramification indexes as 1. And by using the fundamental equality, we can say that zeros and poles, the 0 and the pole of Z in FQ of Z should have the n many extensions in the extension field, where n denotes the extension degree. So that means these places should split completely in the extension F. And the part 3 is an immediate consequence of the part 2, because in part 3, what we claim is that like the minimum distance is bounded below the square root of the gonality, and gonality was the minimum extension degree over a rational function field, right? Is a rational subfield. And in part 2, what we have seen is that like this minimum distance is like the square root of, like square of the minimum distance of Z is bounded below Z times degree Z, and Z degree Z is indeed equal to the extension degree F over FQ of Z. And we know that by the definition of the gonality, this should be always bigger than or equal to 2 times the gonality of our function field. And by taking the square root, we can see the desired property. So you are taking the minimum all over the non-zero vectors or non-zero functions. So the minimum distance of our function field lattice is bounded below the square root of 2 times the gonality. And we will see that in the next proposition, our function field lattice is a subspace lattice of an minus 1, and we compute its rank, and we try to investigate what we can tell about its determinant.